This video will be about scientific notation. So scientific notation is useful if you have a very, very large number or a very, very small number. So when we have a lot of zeros going on, and it doesn't have to have zeros, but when you get really, really big numbers or really, really small numbers, it's a lot of stuff to write out. So they came up with a way to represent this without having to use so many zeros. So let's take a slightly smaller number to see why we do what we do. Let's take 370 instead of this whole big thing. So 370, that's the same as 37 times 10. 37 times 10 makes 370. We could take that one step further and say, well, 3.7 times 10 again makes 370 as well. So when there's two of them, we would rewrite it as 3.7 times 10 to the second power, because there were two 10s. So we do that, and when we do our scientific notation, we always want the decimal behind the first digit. So first digit was a 3, we're going to put the decimal here, or first digit besides the zeros is a 5, so we'd want the decimal here. And then we count how many times. So we want the decimal here, this is where we want it to be. Currently on 370, the decimal starts here. So from how far it starts to where we want it, we go 2 digits over. 1, 2 spaces. That's another way to get that number that goes as the exponent. Because we don't want to have to split it up this long way every time. We want a quick, easy way to just count. So like 370, whatever this long number is, we want the decimal here. But it starts at the end right now, so we count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spaces. So this is 3.7 times 10 to the 12th. Now if you start with a really, really small number, this time we're going to be counting going towards the right. That'll make our exponent negative. So we start here, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spaces. So 5.23 times 10 to the negative 11. So when you move the decimal to the right, you're going in the negative direction. When you're moving the decimal to the left, you're going in the positive direction for the exponent itself. So one more example. Let's say we have 0.00412. We want the decimal to be right after that first digit that's not a 0, 4, and we just count. 1, 2, 3 spaces. So 4.12 times 10 to the negative third. We went to the right, so we're getting a negative exponent. So we can also go backwards. They can give us something in scientific notation, and we need to write it in standard notation. So let's say we have 1.57 times 10 to the third. And we want to write it in standard notation. So to make a positive exponent, we moved from the right to the left. To undo it, we're going to move back to the right. So our decimal, we wanted it here to make it scientific notation, but now we're going to move it back to the right. 3 spaces, 1 space, 2 space, 3 spaces, and there's a blank space. Yeah, the X got in the way, but let me write it to the side so it's not, we're not getting confused with that multiply sign, 1, 2, 3. So if there's an empty space where we have another digit before our decimal, we just put a 0 back in. When we put it in scientific notation, we take the zeros out. When we put it back in standard notation, we put the zeros back in. So 1,570 would be 1.57 times 10 to the third in standard notation. And if you have a negative exponent, instead of moving this way, you'd go back to the left. So let's say we have 5.7 times 10 to the negative 5th. So we're going to take that 5.7, since it's negative, we'll be going to the left to undo it. 3, 4, 5 spaces. So our decimal will start here now, and we have 1, 2, 3, 4 zeros, and then 5, 7. And the decimal moved, so we don't need a decimal after the 5 anymore. So 0.000057. So we can also take our scientific notation and order it from least to greatest. Say we have 4 numbers in scientific notation already. We want to order them from least to greatest. So the first thing to do is to look at the exponents. The exponents can tell us right away what's smaller, what's bigger. So the smaller your exponent is, the smaller your number is. The bigger your exponent is, the bigger the number is. So our exponents are 16, 15, 16, and 14 over here. Sorry, it got kind of smushed at the end. So the smallest exponent is a 14. That's the first number, 7.35 times 10 to the 14th. Our biggest exponent is 16, but there's 2 of them. So both of them might be the biggest. We're going to decide on that in a second. So 15's in the middle. It's definitely bigger than the exponent of 14. So even though 7.35 is bigger than 3.75, if we were to write these all the way out, 7.35 would end up with 1 less 0 than 3.75. So it's actually smaller. So those exponents tell us first, what's least, what's biggest. Second, if you do have a matching exponent like our 16s, now you compare the numbers in front. So since 16 is matching on the exponents, we say, okay, well 1.5, that's smaller than 2.143. So 1.5 would be next, and 2.143 would be the biggest. So you can also take exponents and scientific notation and order them from least to greatest, even if it's not already in correct scientific notation. So let's say we have 63.2 times 10 to the negative 6. 64 times 10 to the third. 0.065 times 10 squared. 6.37 times 10 to the negative 3. So we can put these in order, but notice not all of them are in correct scientific notation. Just because you have 10 times 10 to the something doesn't make it correct scientific notation. Here the decimal should be after the 6. Same thing here, it should be 6.4. Here it should be 6.5. So we've got to change this. So we move 1 to the left. When you do that, you're going up. You're getting bigger, so you add 1 to the exponent. Negative 6 plus 1 is negative 5. Same thing here. 64 has decimal here. We move 1 to the left. 6.4 times 10. We add 1 to the 4th. This one we're moving to the right 2 spaces. So we get 6.5 times 10 to minus 2 is 0. When you have 10 to the 0, you actually get rid of that completely and you just have 6.5. And then 6.37, that's already in correct notation, so we just leave it. So now we put these in the correct order. We look at the exponents. We have a negative 5, a 4, a 0, and a negative 3. Negative numbers, the negative 5 is smaller than the negative 3. So negative 5 is the smallest exponent. 6.32 times 10 to the negative 5 goes first. Okay, between 4, 0, and negative 3 is the smallest, so 6.37 times 10 to the negative 3. Between 4 and 0, 0 is smaller, so 6.5 comes next. And then 6.4 times 10 to the 4th would be the greatest. So the last thing we can do with scientific notation is some multiplying. So let's say we have 3.7 just regular decimal number, not in scientific notation, times 5.1 times 10 to the third, which will be in scientific notation. So when you multiply a regular number times a scientific notation, you multiply the numbers in front together, 3.7 times 5.1. That would give you 18.87. The times 10 to the third you'll just bring down. So this is currently not in correct scientific notation. We need to move the decimal 1 to the left, which means we will add 1 to the exponent. Times 10 to the fourth would be our correct final answer. They might also ask this as a word problem. So let's say in 2010, the population of the US will be about 3.09 times 10 to the 8th. Spending for healthcare will be about $8,754 per person. How much is the US spending on healthcare in 2010? So if this is per person, and this is how many people there are, then we need to multiply them together. We're going to multiply the 8,754 times 3.09 times 10 to the 8th. Again, we just multiply the numbers in front of the times 10 to the 8th stuff together. So 8754 times 3.09 is 27,049.86. And we still have times 10 to the 8th. So now we need to adjust our scientific notation. We have 1, 2, 3, 4 moves to put our decimal in the correct spot. So we add 4 to the exponent. We need 4 more 10s. So we have 2.7. Sometimes when there's like a 0 immediately after, they'll just round here. 2.7 times 10 to the 8th. Oops, sorry. I needed to add 10 to the 12th now. 8 plus 4 is 12. So they could leave it like this instead of, rather than still having a whole bunch, 0, 4, 9, 8, 6 times 10 to the 12th. Because we are trying to simplify this and make it as easy to write out as possible. So that concludes our discussion on scientific notation.